So in this lesson, we're going to be talking about something called optimization, and optimization is something about maximum and minimum values, and they come up all the time in real-world applications like business applications or economic applications where you might want to, maximize the product or minimize the cost or something like that. And so we are going to define a couple of things here. So first of all, linear programming. Linear programming, this is kind of a long one. It's a method for finding maximum or minimum values It's a bad pen. Values of a function over a given system of inequalities each representing a constraint. Okay, so this definition, first of all, kind of reminds me of what we saw in the last notes with Mr. and Mrs. Rodriguez driving. So you're finding maximum and minimum values over a given system of inequalities. So picture those inequalities where you said, like, all right, combined, the Rodriguez are going to drive no more than 10 hours, and Mr. Rodriguez wants to drive between these two values, Mrs. Rodriguez wants to drive between these two values. That's what it means by each representing a constraint. You can't go any farther than that in one direction. So a feasible region. The feasible region is the vertices of the solution set. The vertices of the solution set. So we've got two different feasible regions. We've got a bounded feasible region and an unbounded feasible region. So unbounded looks something like this, where you've got, like a line right here, and you've got a line right here, and you've got a line right here, and you've got these vertices, and the shaded region is everything in between. So it's bounded. So you've got these lines that you can't go outside of that region. And then something unbounded would look like this. Maybe you've got a constraint right here, and you've got a constraint right here, and you've got a constraint right here, but they don't all meet like that. So you do have vertices here, but your graph is going to be unbounded in one direction. So two different options there. So the feasible region is everything shaded in here, bounded by these vertices. This unbounded region still has this whole feasible shaded region, but the feasible region goes on forever. So example 1, we're going to graph the system of inequalities, name the coordinates of the vertices, and then find the max and minimum values of the function for this region. All right, so we are going to look at these two values right here. So set up our system of inequalities. So start with this first one. This one is saying that x has to be between two different values. So start with an x value of -2, and then go up to an x value of 6. So it first says that x has to be in between those two values. Now notice it's got less than or equal to's. So that means that we do a solid line, and then we're going to be shading everything in the middle. So I'm going to hold off on a second on the shading because I want to get my whole region. I want to shade just the overlapping parts when we're done. Okay, so next, y has to be between two certain values. So here's y equals 1, and then up 2, 3, 4, 5. So we've got to be between y equals 1 and y equals 5. So far, we've got to be in this rectangle right here. That's in between these two vertical lines, in between these two horizontal lines. And then we graph this last one right here. So this one it's in slope-intercept form. It's got a y-intercept of 3, so I start right there. And then it's got a slope of 1, because there's technically a 1 in front of the x. So I go up 1 to the right 1, up 1 to the right 1. And then I graph a solid line, because this is less than or equal to. So graph that line right here. And then it's less than, so let's test this one. because it's either going to be this little triangle or this rectangle with the triangle missing. So let's test it out. So is 0 less than or equal to 0 plus 3? Question mark. And yes, that is true. 0 is in fact less than or equal to 3. So I would shade towards the origin, towards 0, 0. So my final region is going to be in the rectangle that I already marked out, and then underneath that diagonal line. So everything in this shape right here. So that is my feasible region, and it's marked by these vertices. So I need to identify exactly what those vertices are. So I've got one right here, right here, right here, right here, right here, and I need to identify all of those points. So first thing is I want to identify each one of the vertices. So right here I've got the point 0, 1. That is right on the y-axis. That is the point 0, 1. Right here I'm up at 3, so this is 0, 3. Right here I'm over 1, 2 units and up 5 units. So that is the point 2, 5. Here I'm over 6 units and up 1. So that is 6, 1. And here I'm over 6 and then up 5. So this is 6, 5. All right, so that's the first thing you do, is you plot however many inequalities you're given. Here I had 3 inequalities. I plot them all, I get my shaded region, and then I identify all the vertices, all right, which is kind of where my region is bounded on each side. So I write down all those vertices. Last thing I do is I evaluate this function at all of those values. Okay, so that's how I find the maximum and minimum values of the function. So this is a function of x and y. It's something that I haven't seen before. It brings kind of a third variable into the situation here. And so when I want to plug in my x and y coordinate points, I plug in my different x and y's. So say I plug in first 0, 1. I'm going to plug 0, 1 into this equation right here. So I have negative 5 times 0, and then plus 2 times 1. So this gives me 0 plus 2. So when I plug in 0, 1, I get 2. Next point, I'm going to plug in 0, 3. When I plug in 0, 3 into this equation, I get negative 5 times 0, and then plus 2 times 3. This, of course, is again just 0, and then 2 times 3 gives me 6. So keep moving my way around this shape. Next, I'm going to plug in 2, 5. So when I plug in 2, 5, I have negative 5 times 2, and then plus 2 times 5. So negative 5 times 2 is negative 10, and then 2 times 5 is 10. So when I combine those up, I actually get 0, negative 10 and positive 10. Next one is up here, 6, 5. So plug that in, so negative 5 times 6, and then plus 2 times 5. So negative 5 times 6 is negative 30. Plus positive 10, so I get a negative 20. And then last is 6, 1. So I plug in negative 5 times 6, and then plus 2 times 1. So this is a negative 30 and a positive 2, so that gives me a negative 28. So what I'm trying to identify is the maximum and minimum values of the function. So here is the minimum value of the function, and here is the maximum value of the function. So what we list is we would say that the max is at 0, 3, and that the min is negative 28 at 6, 1. So that is how we'd write out our final answer. We've got a maximum value and a minimum value that are listed right here. All right, so I am going to actually skip over the next problem. We're just going to jump right into the next section here, because I think that these, they take a little bit for me to explain. We'll see how long the video ends up being after we go here. So graph the system of inequalities, same directions. Name the coordinates, find the maximum and minimum values. So let's start with this one. X has to be less than or equal to 8. I'm sorry, y has to be less than or equal to 8. So let's go up to a y value of 8. Let's go 2, 4, 6, 8. So this is going to be a solid line where y is 8. And then if we want everything underneath. All right, so we've got Everything underneath, these are all the y values that are less than or equal to 8. I'm not going to shade anything too dark there, but I know it'll be underneath this horizontal line. Next one, y has to be greater than or equal to negative x plus 4. So I start with my y-intercept of 4, and then I have a slope of negative 1. So if we scale this as well, 2, 4, 6, etc. So if I go down, technically I go down 1 to the right 1, but I could also go down 2 to the right 2. That would also be a slope of negative 1. So again, I go down 2 to the right 2. This is going to be a solid line because I have a greater than or equal to. So I could also go, let's see, up 2 to the left 2, up 2 to the left 2. That way I know where this point is because I'm going to need to know that vertex. All right, so I connect those dots, again using a solid line because this is a greater than or equal to. And then I'm going to test 0, 0. So is 0 greater than or equal to negative 0 plus 4, question mark, and that is false. So that means I shade away from the origin. So next I've got this region shaded. So far I've got in between these two lines, this whole region right here is shaded. Next, y has to be less than or equal to negative x plus 10. So I go up to a y-intercept of 10. So here's 2, 4, 6, 8, 10. And then I'm going to have a slope of negative 1. So I go down 1, I'm sorry, I guess down 2 to the right 2, down 2 to the right 2. This is going to be a solid line because I have the or equal to. So it looks like that. Now notice that these two lines run parallel, which should make sense because look at their slopes. They both have slopes of negative 1, so they're going to run parallel. So let's test 0, 0. Is 0 less than or equal to negative 0 plus 10? Question mark. So again, is 0 less than 10? Yes, it is. So I would shade everything underneath that line. So here's what I have so far. It's in between, I'm sorry, it's underneath this line right here, and it's now kind of in between these two lines. That's what I've got so far. All right, and so my overlapping region, like I said, is everything underneath this line and in between these two lines. So when I shade my final region, it gets bounded above by this y equals 8, but then I can shade everything in between these two lines, and it just keeps going down and down and down and down. So it's unbounded. It goes way down as far as I can imagine, but it stays in between these two lines. So for the minimum and maximum values, when we're talking about an unbounded region here, we really only have two vertices that we can plug in. I guess we've got one right here. So we can plug in the vertices here, here, and here. When we are looking at each vertex, we are still going to mark on the vertices that we can, where it kind of stops in one direction. So like these two are going to be vertices because it stops right here. So here I have a value of negative 2, negative 4, up 2, 4, 6, 8. So this is negative 4, positive 8. I'm going to have another one right here. This is 2 and then up to 8. And then really I actually just keep going forever in both of these directions. So I thought for a second that that might be a vertex, but it's not because we keep going this way. So really we are only going to have the 2 points there that bound our region in any direction. And so it's going to keep going like that. So when I plug in these 2 points, I'm going to plug in the point negative 4 eighths. I'm going to plug it right into this function right here. So I have negative 6 times negative 4 and then plus 8 times 8. So that gives me, this is a positive 24 and then plus 64. So that gives me 88. So when I plug in negative 4, 8 into this function with 2 variables, I get an 88. And then I can plug in 2 comma 8s into the very same function. So negative 6 times 2 and then plus 8 times 8. I get a negative 12 and a positive 64. So when I combine those up, I get a positive 52. So here's my maximum value, here's my minimum value. Again, remember I only had the 2 values to work with. So I get a max of 88 at negative 4 comma 8, and then I get a minimum value of 52 at 2 comma 8, and then it's unbounded, so it almost makes our work a little less when we have an unbounded region because we don't have to check 2 more points the way we did with this one. We actually had 5 vertices to check here, so it's more work for us really if the region is bounded. All right, so now let's look at this optimization stuff here. All right, so to optimize, that's kind of what I was talking about at the beginning. So to optimize, this means to seek the best price or amount to minimize costs or maximize profits. Okay, so obviously, when we're talking business or when we're talking economics, we would like to optimize these different variables. We would like the cost to be at a minimum, we'd like the profits to be at a maximum, things like that. So we're going to look at one specific real-world example here. So optimization with linear programming. We will kind of go through, we'll write down the steps and then go through and do this problem. So step one is to define the variables. Okay, so figure out what variables we're looking for and then define them. So each week, Mackenzie can make 10 to 25 necklaces and 15 to 40 pairs of earrings. If she earns profits of $3 on each pair of earrings, $5 on each necklace, plans to sell at least 30 pieces of jewelry, how can she maximize profit? So we've got two variables to define. We've got the number of necklaces and the number of earrings. So let's write N equals the number of necklaces, and then E equals the number of earrings. Okay, so that's the first step. We have defined our variables. So back up into the steps. Step two is to write a system of inequalities. And that's the tricky part with these, is that the ones that we had on the previous 2 pages, we weren't coming up with the equations, they were given to us already. Here, we've got to kind of go off the story problem and make these up. So each week, Mackenzie can make 10 to 25 necklaces. So that's actually going to look exactly like these variables right here, when X was between 2 numbers, Y was between 2 numbers. So here, N is going to be between 10 and 25. So she can make at least 10 necklaces, no more than 25 necklaces. That's our first one. Next one, she can make between 15 and 40 pairs of earrings. So we put our variable E in between 15 and 40. We do the less than or equal to's because it said she can make 15 and she can make 40. So it's not that we don't include those two values. Next, we've got profits of $3 on each pair of earrings and then $5 on each necklace. That's going to be our profit function. The next one we need to set up actually is the 30 pieces of jewelry. So she plans to sell at least 30 pieces of jewelry. So the number of necklaces plus the number of earrings, she plans on that being at least 30. So remember, least always tricks us a little bit, makes us think it's going to be a less than, but when she wants at least 30, that means she wants 30 or more. So the last one, this is going to be the important one, the profits function. So let's say the profit, and then in parentheses, notice here how I had f of x and y. It was a function of the variable x and the variable y. Our profit is going to be a function of the number of necklaces and the number of earrings. So by that I mean the profit is going to be affected by how many necklaces she sells and how many earrings she sells. It's not just a function of one variable. It's not just a profit involving one variable. So she earns $3 on each pair of earrings. So $3 per pair of earrings, and then plus $5 per necklace. So that is a function that represents the profit that she's going to make depending on how many she sells. All right, so up here, back to our steps. Step 3, graph the system of inequalities. Okay, so we're going to set up some graphs here. We have N and E as our variables. So anytime we have random variables like this, remember it doesn't really matter where you mark your axes. Keep in mind, though, that neither N nor E can be negative. I can't have a negative amount of necklaces, nor can I have a negative amount of earrings. So I'm just going to put N here and E here. Doesn't matter if you go the opposite way. So they can't be negatives. There's no point in going any farther to the left or any farther down. So when I set up my variables right here, n has to be between 10 and 25. So let's go 5, 10, 15, 20, 25. So here's the 10, here's the 25. So I can go somewhere in between 10 and 25. So the number of necklaces that she can sell or that she is going to make are somewhere in there. That's my first inequality. Second inequality, E, is going to be between 15 and 40. So for this one, let's go 10, 20, 30, 40. All right, so here is the 15, halfway between 10 and 20, and then here's the 40. So again, these are going to be solid lines because I have the or equal to. So start with 15, go up to 40, and it can be anywhere in between these two values. So now what we have so far is a little rectangle right here. This is the number of necklaces and earrings that I will make somewhere in here. Third one that I'm going to graph, n plus e has to be greater than or equal to 30. So when I'm graphing this, I'm going to graph using intercepts. So my n-intercepts, remember the way I find my n-intercept is if I set e equal to 0. So if I set e equal to 0, then n is 30. So that is my n-intercept, which I'm going to plot right there. So what that means is if she sold no earrings at all, how would she make her 30 pieces of jewelry? Well, that would be by making 30 necklaces. She's not going to make 30 necklaces because that's outside her range, but we're still going to use this point to plot the graph. Next, so this is n equals 30. And then the e intercepts, again, we do the opposite. We're going to plug in 0 for n. This would be how many earrings she made if she was going to make all 30 pieces of jewelry earrings. So E would be 30. So we plot this point right here. So here's the 30, because this is 10, 20, 30, 40. So there's 30 on the E-axis. So I can mark this as 30, can mark this as 30. And then I just connect those two dots using a solid line, because this is greater than or equal to. And remember, we are going to plot that as a segment. We don't go any farther this way, any farther this way. And finally, I am going to test the point 0, 0. So is 0 plus 0 greater than or equal to 30? No, that's definitely false. So that means that I shade away from the origin, so I shade up here. So my final region has to be between these 4 straight lines and above this diagonal line. So here's what I end up with. It's inside this rectangle, but above that diagonal line. And so we cut out a little bit of the rectangle, because this bottom left-hand corner, I wouldn't be making at least 30 pieces of jewelry. So this is what I set up here. All right, so I graph my inequality. Step number 4, find the coordinates of the vertices. Of the feasible region. Okay, so find the coordinates of the vertices of the feasible region. So back here, so I've got a vertex right here, a vertex right here, a vertex right here, here, and here. So I can mark those all right on there. It's like this one right here, for instance. Actually, let's start with the edges because these ones are easier. This is 25 and 15. This one up here is 25 and 40. This one right here is 10 and 40. And now these ones are going to be a little bit trickier to find. What I need to do is for this one right here, I actually need to plug 10 into this function to figure out what I'm going to get. So if I plug 10 into this line right here, 10 plus what gives me 30? Well, that would be 20. So that must mean that this is 10 comma 20. And then right here, I need to plug E equals 15 into this equation. So what plus 15 gives me 30? Well, that would be 15. So this is 15 comma 15. All right, so all 5 of these vertices match all of her inequalities perfectly. So like this vertex, for example, is when she makes the most necklaces that she can and the most earrings that she can. Here is when she makes the most necklaces she can and the least earrings she can. Right here, she makes somewhere in between the most and least, but it falls on this line where combined she makes 30, because here 10 and 20 gives us 30, 15 and 15 gives us 30. So these are all 5 vertices that could work to make a maximum value. So back to our steps. So step 5, write a linear function to be maximized or minimized. We already did that. Write a linear function to be maximized or minimized. That's actually this guy right here. That is our linear function that we're going to maximize or minimize. It has to do with her profit. Plug the vertices into the function. Okay, so we've got 5 vertices right here to plug into the function. All right, so let's plug them all in. So start with 10, 40. So if I plug in 10, 40, I've got 3 times, and then the number of earrings, careful, I'm backwards here. The number of earrings is actually 40, and then plus the number of necklaces is 10. So this is $120 plus $50, that's $170. So if she makes 10 necklaces and 40 pairs of earrings, then she would make $170. Next one, top right, 25, 40. So again, necklaces come first. So that would be 40 pairs of earrings plus 25 necklaces. So that would be $120 plus $125. So that would be $235 that she would make if she made 25 necklaces and 40 earrings. Next, bottom right is 25, 15. 25 necklaces, 15 pairs of earrings. So 3 times 15 plus 5 times 25. So 3 times 15 is 45. And again, 5 times 25 is 125. So that would make her also $170. Then move over here to 15, 15. That would be 15 pairs of earrings and 15 necklaces. Oops, that should be a 5. So 3 times 15 is 45. 5 times 15 is 75. So 45 and 75 is 120. And last one, we can plug in this point right here, the 10, 20. Okay, so remember that is 20 earrings, because these ordered pairs are switched, plus 10 necklaces. So this is $60 on earrings, $50 on necklaces. That makes her $110. Okay, so we plugged all our vertices in. This is the profit for all of these different values. Last thing, number 7, is to identify the max or min. Okay, so she is trying to maximize her profit. So this right here would maximize the profit. So she says, how can she maximize profit? Well, that would be by selling 25 necklaces and 40 pairs of earrings. And that would maximize her profit. All right, so that would be your final answer. Always make sure you're answering whatever they asked you. They want to know how they maximize profit, and this would be how. All right.